This lesson covers the reasons for aerodynamic balance of flight controls and the various methods that are employed to achieve this balance. The aerodynamic force acting on a control surface through its centre of pressure would tend to rotate the control around its hinge in the direction of the force. The moment produced will be the force F multiplied by the distance d from the hinge to the centre of pressure. This is known as the hinge moment. The aerodynamic force will vary with the angle of deflection of the control surface, the size of the control surface, and the speed squared. The size of the control surface is usually fixed. However, as speed increases, the aerodynamic force generated greatly increases. To move the flying control surface to the required angular displacement and maintain it in that position, the pilot has to overcome and then balance the hinge moment by applying a force to the cockpit control. The cockpit control load or stick force will therefore depend on the size of the hinge moment. Up to a point, this is a good thing, as it produces feel in the controls. However, for large and fast aircraft, the resulting force could give hinge moments and related stick forces which will be too high for easy operation of the controls. The pilot will require assistance to move the controls in these conditions, and this can be done by using mechanical advantage or by power operation, both of which will be discussed in another lesson, or by using a system to reduce or oppose the moment. Modern large aircraft have flight control systems operated by hydraulic power. However, smaller aircraft will have a mechanical system where the pilot provides the motive force. Having moved the control surface, he will have to maintain a force on the control to oppose the aerodynamic force, which will be attempting to reverse the operation and return the surface to the neutral position. For this reason, manually operated flight controls are known as reversible controls. Aerodynamic balance is a common method of helping the pilot of an aircraft with manual controls to move the controls while still leaving him with a reasonable amount of feel. Aerodynamic balance involves using the aerodynamic forces on the control surface to reduce the hinge moment. It may be achieved in several ways, and we will now have a look at some of the methods used. The first method we should look at is called the inset or setback hinge. Setting the hinge back in the control surface puts it nearer the centre of pressure, causing the hinge moment to be reduced. Furthermore, the airflow strikes the surface forward of the hinge, exerting a force which opposes the hinge moment and helps the pilot move the control. Setting the hinge back does not reduce the effectiveness of the control. Only the hinge moment of the force is reduced, not the force itself. It is important that the centre of pressure is not moved too close to the hinge line, as when a control is operated, its centre of pressure moves forward. If this was to take the centre of pressure forward beyond the hinge line, then all feel would be removed, or even reversed. The principle of horn balance is similar to that of the setback hinge. The horn is part of the control surface and is forward of the hinge line. In flight, when the control surface is displaced, as shown in the diagram, aerodynamic forces will be generated both fore and aft of the hinge line. This produces turning moments about the hinge, reducing the overall hinge moment. Once again, control effectiveness is unaffected. Design of the horn balance will mean that during operation, the horn extends above or below the surface of the main aerofoil section. This will cause an increase in drag. Horn balance is commonly found on rudders and elevators. Internal balance works on the same principle as the setback hinge, but the balancing area is enclosed inside the rear of the main aerofoil section. This forms a chamber split into two halves by a flexible diaphragm, the areas of which will feel the same changes in pressure as are produced above and below the control surface. The pressure differential inside the chamber will produce a moment in opposition to the hinge moment. In our example, the control surface is moved down. Pressure above the aerofoil is reduced, and pressure below it is increased. The reduced pressure is felt on the upper surface of the balance, and the increased pressure on the lower surface. The pressure difference on the balance therefore gives a hinge moment which is in opposition to the hinge moment on the main control surface, and the overall hinge moment is reduced. The advantage of this system over the previous two is that because the balancing area is inside the wing, there is no increase in drag. All of the previous solutions provide balance by causing some of the pressures on the control surface to act forward of the hinge line. Stick force can also be changed by small aerofoil tabs positioned at the rear of the control surface, but these do alter the effectiveness of the flying control. There are four main types of trailing edge tab device. They are the balance tab, the anti-balance tab, the spring tab, and the servo tab. These tabs are small aerofoil sections hinged at the trailing edge of the flying control surface. Their actual size will vary from aircraft to aircraft. We will now take a look at each of these tabs in greater detail. We will first consider the balance tab. The pilot has no direct control over tab movement. The pilot's inputs to the flying control are transmitted by a linkage to move the balance tab in the opposite direction to the flying control surface. The pilot moves the control surface moves the tab. The balance tab generates an aerodynamic force in the opposite direction to the flying control surface. This reduces the hinge moment and stick force, but will also give some reduction in control effectiveness. Aircraft fitted with large elevators or stabilators are capable of generating very powerful aerodynamic forces due to their large surface area. For relatively small control deflections, especially at high speeds, the forces produced could cause the pilot to over-control. If this were the case, an increase in stick force would reduce the possibility of over-controlling. This can be achieved by the use of an anti-balance tab. You can see from the graphic the similarity between a balance and an anti-balance tab. The difference is that the arrangement of the control linkage causes the anti-balance tab to move in the same direction as the control surface. It can be seen from the graphic that both the tab and the control surface force act in the same direction. Anti-balance tabs are commonly used on all flying tailplanes, otherwise known as stabilators. Remember, the balance tab reduces stick force, while the anti-balance tab increases it. The servo tab is used to assist the pilot in moving the control surface. It differs from the previous two tab controls in that the pilot actually controls the tab and not the control surface. Movement of the tab generates an aerodynamic force which moves the main flying control. View the sequence of events in the graphic, which depicts an elevator with a servo tab attached. As the pilot selects a nose-up pitch, note that to pitch nose up, the tab moves down, causing the elevator to move up. This does not affect the way the pilot operates his cockpit controls. You can use your mouse to step through the operation of the servo tab. Each click in the box will move it forward one step. If the aircraft is stationary on the ground, movement of the cockpit control will give no movement of the control surface, only of the tab. The control becomes effective as speed increases. It should also be noted that if external control locks are fitted to the control surface, the cockpit control will still be free to move, as the tab is not normally locked. Servo tabs tend to be used on larger aircraft, where the weight, due to the physical size of the flight controls, let alone their aerodynamic forces, will produce very large stick forces. The Boeing 737, for instance, normally uses hydraulic power for its flight controls, but has servo tabs as a backup in the event of hydraulic system failure. The final tab we are going to look at is the spring tab. It is a modification of the balance tab, such that the tab movement is proportional to the applied stick force. Maximum assistance is therefore obtained when the stick forces are greatest. This is achieved by putting a spring in the linkage to the tab. The spring tab is used mainly to reduce control loads at high airspeeds. The pilot's control movement is transmitted to a lever pivoted on the primary control surface, but not directly operating it. Operation of the control surface is via springs. With low aerodynamic loads, the springs are strong enough not to be compressed, so the control surface moves with control input, and there is no change in the position of the trim tab relative to the control surface. The full load is felt by the pilot. As the aerodynamic loads increase, the spring force will be overcome, causing the balance tab to move in the opposite direction to the primary control surface, thus reducing the stick forces. There is one more form of balancing that is applicable to flying control surfaces, but this time it has nothing to do with assisting the pilot to operate the controls or to reduce stick force. It is known as mass balancing, and its purpose is to reduce control surface flutter. Flutter is a phenomenon associated with the higher speeds of aircraft. It is an oscillation of the control surface, coupled with an oscillation and bending or twisting of the wing, fin or tailplane. It can occur on aircraft with manual or powered flight controls. Flutter is likely to occur if the centre of gravity of the control surface is behind the hinge line. Uncontrolled flutter can cause structural failure. Flutter can be prevented by moving the centre of gravity of the control surface onto its hinge line by adding weights to the control. This reduces the inertia moments about the hinge line. This is known as mass balancing, and it can be applied to elevators, ailerons and the rudder. Common methods of mass balancing are shown in the picture. This picture shows the mass balancing of the aircraft's ailerons. That is the end of the lesson on aerodynamic balance. Remember that manually operated flight controls are known as reversible controls. Shown on the screen is a list of all the balance systems discussed in this lesson. You can click on a system to see a short summary of its purpose and operation.